In 1947, on the glaring white expanse of the Bonneville Salt Flats, a British driver named John Cobb strapped himself into a teardrop-shaped aluminium shell called the Railton Mobile Special. He was about to run at 394 miles per hour. The shock of that day was not just the sheer, terrifying speed. It was the machinery making it possible. Beneath the futuristic bodywork sat two Napier Lion W12 aero engines. They were not a new invention. The basic architecture of those blocks had been drafted in a West London factory in 1917, designed to power wooden canvas biplanes over the trenches of the First World War. 30 years later, stripped of their military purpose and heavily supercharged to produce over 1,300 horsepower each, they were still dictating the absolute limits of human speed. By the time Cobb made his record run, the Napier Lion was no longer a cutting-edge aviation secret. It was a piece of military surplus. The Royal Air Force had moved on to leaner V-12s. Napier Son, the company that had built the engine, was steadily losing its grip on the sky. The Lion had retreated from frontline squadrons into marine rescue boats, and finally into the hands of independent record chasers who bought the cast-off blocks simply because they offered brute, cheap power. That was the paradox of the Napier Lion. The engine that made Britain the undisputed fastest nation on Earth, on the water, in the air, and across the salt flats, was an obsolete relic, abandoned by the very aviation system it had helped build. But the real story of the Napier Lion is not only the story of a land speed record, it is the story of how an engine made Britain the fastest nation on Earth, before the very shape of that engine forced its maker into a trap it could not escape. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in the machine shops of Acton, West London, in 1917. In 1917, the skies over Europe were governed by a brutal, unforgiving mathematical equation. The heavier the engine, the slower the aircraft. The Royal Flying Corps, the precursor to the Royal Air Force, was desperately trying to maintain air superiority, but British engineering was hitting a physical wall. The primary source of British aviation power had been the rotary engine, an engine where the entire cylinder block spins around a stationary crankshaft to aid cooling. In a British canvas hangar on the Western Front, the rotary meant extreme gyroscopic forces that made aircraft difficult to turn, massive castor oil consumption that sickened pilots, and a hard absolute limit on how much power could be squeezed from the architecture. To fly faster, carry heavier payloads, and climb higher, Britain simply needed more cylinders. The obvious industrial answer was a V12, a 12-cylinder engine arranged in two banks in a V-shape. But early V12s suffered from a fatal mechanical flaw: the crankshaft. The crankshaft, the rotating shaft that turns piston motion into rotational power, had to be incredibly long to accommodate 6 cylinders in a row. Under extreme combat loads, a long, early 20th century steel crankshaft tended to twist, vibrate, and eventually shatter mid-flight. Britain needed 12 cylinders of power, but it could not afford the weight or the fragility of a long engine. In Acton, West London, the firm of Napier Son watched this problem closely. Before the outbreak of war, Napier was a prestige automotive manufacturer, building luxury motor cars that rivaled Rolls-Royce for silence and mechanical refinement. But the demands of total war meant that luxury was paused for national survival. The British Air Ministry needed power, and Napier had the machine shops, the foundries, and the skilled labor to provide it. Inside the Acton drawing offices, a brilliant engineer named Arthur John Rolls-Royce proposed a radical solution to the V12 problem. If the enemy of reliable power was crankshaft length, the answer was not to forge a thicker, heavier shaft, but to completely change the shape of the engine. Rolls-Royce drafted an architecture known as the W12, or the broad arrow, an engine with 12 cylinders arranged not in 2 long banks of 6, but in 3 shorter banks of 4. All 3 banks would share a single, incredibly compact crankshaft. The broad arrow layout was a masterclass in mechanical packaging. By placing a central vertical bank of 4 cylinders and flanking it with 2 outer banks angled at 60 degrees, Rolls-Royce created a 12-cylinder power unit that was scarcely longer than a standard four-cylinder car block. In a British machine shop, this meant the crankshaft could be short, thick, and brutally stiff, rendering it almost entirely immune to the catastrophic torsional vibrations that plagued longer engines. But the architecture alone could not fly. To meet the Air Ministry's strict weight limits, Napier had to master the dark art of aluminium casting. At the time, casting complex heat-stressed engine blocks out of aluminium, a lightweight metal prone to porosity and cracking, if not poured perfectly, was immensely difficult. Napier's foundry workers managed to cast intricate cylinder heads and water jackets from aluminium alloy, which were then bolted to individual steel cylinder barrels. The resulting engine, named the Napier Lion, was a physical contradiction. It looked massive and impossibly wide, yet it weighed only around 850 pounds dry. When the first prototypes of the Napier Lion were tested in 1918, the results sent a shockwave through the British aviation establishment. The engine reliably produced 450 horsepower. To understand that number in the context of the era, the standard British fighter planes of 1917 were flying on engines producing a mere 130 to 200 horsepower. The Lion effectively doubled, and in some cases tripled, the available thrust. It was a leap in mechanical capacity that immediately caught the attention of the British government. The Acton factory, originally built to craft silent limousines for the Edwardian elite, was suddenly transformed into a vital artery of aviation engineering. The casting lines were reorganized, the foundries ran hot, and the smell of industrial oil and machined aluminium became the defining scent of Napier's future. The first production lines were earmarked for the Airco DHA bomber, promising to give British crews the range and speed they desperately needed. By the end of 1918, the First World War ended before the Lion could see mass combat. For many wartime engine programs, peace meant immediate cancellation. The government canceled contracts, factories fell silent, and thousands of workers were laid off. But the Lion was too powerful to be scrapped. The Air Ministry recognized that this short, wide, immensely strong block of aluminium was the key to whatever came next. The block was ready, but to prove its worth, the Lion had to do more than pass military tests. It had to teach a recovering nation how to dominate the skies. In 1919, the British aviation industry faced a sudden, brutal contraction. The First World War had ended, and the Air Ministry, which had previously ordered aircraft by the thousands, immediately slashed its budgets. Across the country, wartime engine builders collapsed, went bankrupt, or retreated to building road cars and motorcycles. Napier and Son stood at a dangerous crossroads. They could easily have returned to their Edwardian roots at their Acton factory, hand-building silent, expensive saloons for the British upper classes. But the Lion W12 was too successful, too powerful, and too deeply entrenched in government testing to abandon. What made the Lion indispensable to the recovering nation was not just its 450 horsepower, but how that power was delivered. The Lion had a massive displacement, the total volume swept by the pistons inside the cylinders, of 24 liters. In a British hangar, this meant the engine did not need to scream at terrifying, unreliable revolutions to generate thrust. Instead, it produced immense torque, the twisting force that gives an engine its pulling strength, at relatively low engine speeds. This allowed aircraft designers to fit larger, more efficient propellers to move heavy loads. Mechanically, the engine was a liquid-cooled masterpiece. A liquid-cooled engine, an engine that pumps water or coolant around the cylinders to absorb and carry away extreme heat, allowed the Lion to operate for hours at high power without the overheating issues that plagued older air-cooled designs. In the machine shops at Acton, the assembly process was intensely demanding. The complex cylinder head, the upper part of the engine that helps seal the cylinders and contains combustion passages, was cast from aluminium and bolted to separate steel cylinder barrels. To feed the three banks of cylinders, engineers had to meticulously tune the carburetor, a device that mixes fuel and air before the mixture enters the engine. Mechanics quickly learned that balancing these carburetors was the key to unlocking the Lion's smooth, relentless power. Recognizing that they had created an industrial phenomenon, Napier's management made a staggering decision. In 1924, they completely shut down their historic automobile division. The Acton factory, with its foundries, machining lines, and highly skilled workforce, was entirely retooled to produce nothing but the Napier Lion. It was a terrifying gamble. The company was staking its entire survival, its workforce, and its heritage on a single internal combustion engine, an engine that burns fuel inside its cylinders to create power. If the Lion failed, or if the Air Ministry found a better alternative, Napier would cease to exist. But the gamble paid off because the British aviation system desperately needed what the Lion offered: mechanical trust. The engine quickly became the beating heart of the newly formed Imperial Airways. At Croydon Aerodrome, mechanics in oil-stained overalls loaded mail and passengers into de Havilland DH-34 biplanes, trusting the single Napier Lion mounted in the nose to pull them safely across the English Channel to Paris. In the early days of commercial flight, an engine failure over water meant an almost certain crash. Passengers and pilots alike listened to the steady, deep thrum of the W12, knowing their lives depended on the machining tolerances of the Acton factory. The Lion rarely failed them. Maintaining a 24-liter W12 was not a simple task. An overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, required specialized jigs, lifting equipment, and mechanics who understood the unique geometry of the broad aeroblock. But the Air Ministry invested heavily in training its ground crews. The Lion became deeply embedded in the service network of the military. Spare parts from Acton flowed into military depots across the country, ensuring that whenever a connecting rod, the part that links the piston to the crankshaft, needed inspection, the aircraft was not grounded for long. This logistical dominance made the Lion incredibly difficult for rival manufacturers to displace. For the Royal Air Force, the W12 became the heavy lifter of a global empire. When the military needed to move troops and supplies across vast, unforgiving distances in the Middle East, they relied on the Vickers Vernon and later the Vickers Victoria, large twin-engine troop carriers powered exclusively by the Lion. In these harsh environments, where sand, heat, and poor maintenance could destroy lesser machines, the Lion proved its durability. The engine's pulling power also caught the attention of a small aviation firm located on the south coast of England named Supermarine. When the RAF needed a maritime patrol aircraft to guard the coastlines, Supermarine designed the Southampton, a massive twin-engine flying boat. Supermarine chose the Napier Lion to power it. This established a vital engineering relationship between Supermarine's chief designer, R.J. Mitchell, and Napier's W12, a relationship that would soon push British engineering onto the global stage. By the mid-1920s, Napier had captured an astonishing share of the British aero engine market. The Acton factory was operating at peak capacity, pouring aluminium and machining steel to fulfill endless government contracts. It is estimated that at its height, the Lion powered over half of all aircraft ordered by the British government. In military hangars, civilian airfields, and maritime slipways, the sound of the Napier W12 had become the defining sound of British aviation authority. It was a safe, dependable, heavy-lifting workhorse, trusted by mechanics with spanners and pilots with their lives. By the mid-1920s, the Air Ministry trusted the Lion for its reliable endurance. But a small group of engineers realized the W12 possessed a very different kind of potential: raw, absolute speed. By the late 1920s, the Napier Lion had transcended its original purpose. It was no longer simply a reliable workhorse for Imperial Airways or the heavy lift squadrons of the Royal Air Force. It had become the physical embodiment of British national pride. In the machine shops at Acton, the workforce understood that they were no longer just building engines for transport. They were forging the weapons for a new kind of global proxy war. This was the era of the Schneider Trophy, an international seaplane race that pitted the finest aviation engineers of Britain, Italy, and the United States against one another. To win the Schneider Trophy was to prove that your nation possessed the absolute limits of mechanical supremacy. The British Air Ministry, desperate to secure this prestige and prove British industrial dominance, threw its full weight in funding behind a partnership that would define the decade: the pairing of Supermarine's visionary aircraft designer, R.J. Mitchell, and the Napier Lion W12. For the 1927 race held in Venice, Napier's engineers took the standard 450 horsepower block and pushed its metallurgy to the breaking point. The racing variant, known as the Lion 7B, was stripped of all excess weight and tuned to run on exotic, highly volatile fuel blends. They radically raised the compression, the squeezing of the air and fuel mixture inside the cylinder before combustion, to extract maximum explosive force from every drop of petrol. The result was a staggering 875 horsepower out of the same 24-liter displacement. In a Britain where an engine could decide whether an aircraft lifted from a grass airfield, a maritime patrol guarded the coast, a racing car survived the salt flats, or a flying boat claimed a global trophy, power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. When Flight Lieutenant S.N. Webster piloted his Supermarine S-5 across the Venetian Lagoon to win the 1927 Schneider Trophy at an average speed of 281 miles per hour, the sound echoing off the water was the brutal, uninterrupted roar of a Napier W12. The victory was a massive propaganda triumph. Acton had proven that its broad aero architecture could beat the best V-Day novels of America and Europe. The engine was suddenly a national hero, splashed across the front pages of British newspapers, celebrated in the trade press, and revered by every mechanic with a spanner. That victory triggered an absolute obsession with the Lion W12 across the British motorsport landscape. If the engine could dominate the skies, British garagistes and engineers reasoned it could also dominate the ground. The late 1920s saw the birth of a unique British pursuit, the chase for the absolute land speed record. In sheds, workshops, and garages across the country, a terrifying new culture emerged. Wealthy drivers and brilliant mechanics began sourcing Lion engines, attracted by the sheer volume of reliable horsepower available in a relatively compact, incredibly rigid block. At places like the Brooklands Motor Racing Circuit in Surrey, the paddock was filled with the smell of hot castor oil and the deafening bark of 24-liter aero engines, bolted into reinforced car chassis. Brooklands was the spiritual home of British speed, a banked concrete bowl where engineers tried to tame aviation power for the road. The Napier Lion quickly became the engine of choice for this extreme motorsport. It was no longer just an aero engine, it was a cultural phenomenon, the default answer whenever a British driver asked how to go faster than anyone else on Earth. The pursuit of absolute speed transformed the Napier Lion from a military aviation tool into a national weapon. In 1928, Captain Malcolm Campbell took his celebrated Bluebird to the sands of Daytona Beach, Florida, to prove British mechanical superiority to the world. Beneath the long aerodynamic bonnet sat a Napier Lion sprint engine, heavily modified by mechanics in British sheds who understood that this 24-liter block could withstand almost unimaginable internal pressures. Campbell reached 206 miles per hour, making him the fastest man on Earth. But the Lion's greatest terrestrial triumph in this era came a year later, in 1929, with Major Henry Seagrave, in a machine known as the Golden Arrow. Built at the Robin Hood Engineering Works in Surrey, the Golden Arrow was a masterpiece of British garagiste ambition. It was powered by a Napier Lion 7A, a block originally prepared for the Schneider Trophy. In this configuration, the unsupercharged engine, relying purely on its massive displacement and high compression, produced an astonishing 925 horsepower. To keep this colossal power plant from tearing itself apart or melting down, the Golden Arrow relied on surface radiators integrated into the bodywork, turning the entire car into a cooling system for the W12. When Seagrave drove it to 231 miles per hour, he cemented the Lion as the ultimate symbol of British mechanical authority. The engine did not just win, it dominated so completely that the car was never raced again. One run was enough to prove the point. The Lion's dominance was not confined to the air or the sand. It conquered the water too. British marine workshops began fitting marinized versions, known as Sea Lions, into high-speed rescue boats and racing craft. Seagrave used a Lion in his speedboat, Miss England, battling against massive American V12s to reclaim the world water speed record. In marine sheds along the British coast, mechanics stripped down salt-corroded W12s, marveling at the thick aluminum castings that refused to warp under the brutal, sustained loads of offshore racing. At the Acton factory, the workforce swelled to meet demand. Machinists who had once crafted delicate components for Edwardian limousines were now pouring continuous streams of alloy for military and racing contracts. The service network expanded across the British Empire. Wherever a Lion flew, from the deserts of the Middle East to the coastal patrols of the English Channel, there was a supply line of spare parts, gaskets, valves, and connecting rods flowing out of West London. The Lion had become an industry unto itself. Entire careers were built around knowing how to set the valve clearances on the 3 separate cylinder banks, or how to tune the carburetors so that all 12 cylinders fired in perfect, deafening harmony. By the end of the 1920s, Napier's engineers had explored every conceivable way to extract power from the 1917 design. They eventually added a supercharger, a mechanically driven device that forces more air into the engine, allowing it to burn more fuel and create more power. With forced induction, the W12's output skyrocketed past 1,300 horsepower. It was a terrifying amount of energy, channeled through steel and aluminum by men wearing flat caps in the Acton machine shops. The public, too, began to view the engine as a living entity. The broad aero layout dictated a very specific triple-humped silhouette on the cowling of any aircraft or car that housed it. To the British public, that triple hump meant speed, reliability, and absolute victory. In the late 1920s, the Lion was the undisputed king of British power. But the very architecture that made it great was about to hit an invisible, impenetrable wall. The first crack in the Napier Empire was not a mechanical failure. It was an aerodynamic one. By 1929, the quest for the Schneider Trophy had pushed seaplane speeds beyond 300 miles per hour. At these immense velocities, the physical rules of aviation changed. Thrust alone was no longer enough. The new enemy was aerodynamic drag. Supermarine's brilliant designer, R.J. Mitchell, was drafting the new Supermarine S6, and he looked critically at the Napier Lion. The W12 layout, with its 3 banks of cylinders, created a massive frontal area, the total cross-sectional surface of an object that pushes against the oncoming air. Pushing the broad arrow shape through the sky at 300 miles per hour was like pushing a brick through a gale. The drag penalty was simply too high. Mitchell needed an engine that was narrow, streamlined, and capable of being hidden behind a sleek, pointed cowling. He found his answer not in West London, but in Derby. Rolls-Royce had developed a supercharged V12 known as the R engine. It was elegantly narrow, cutting through the air with far less resistance. When the Supermarine S6 took to the skies and won the 1929 Schneider Trophy, the Napier Lion was nowhere to be seen. For the first time in a decade, Napier had been publicly and humiliatingly sidelined in the race for absolute speed. The loss of the Schneider Trophy contract was a psychological earthquake on the factory floor at Acton. The British Air Ministry was making its new doctrine clear. The future of frontline military aviation belonged to sleek, aerodynamic airframes. The Napier Lion, despite its phenomenal reliability and massive torque, was structurally obsolete. The very W12 architecture that had brilliantly solved the crankshaft vibration problem in 1917 was now the exact shape that grounded it. That strength had become the trap. Napier's management faced a critical crossroads. They had the capital, the foundries, and the workforce to develop a modern, streamlined V12 of their own to rival Rolls-Royce. Instead, obsessed with minimizing frontal area and desperate to leapfrog their rivals in Derby, they made one of the most fatal engineering decisions in British industrial history. They abandoned the broad arrow layout entirely and gambled the entire company on the H-block. An H-block engine, an engine layout that essentially stacks 2 flat engines on top of each other with 2 separate crankshafts geared together to drive a single output shaft, offered an incredibly narrow frontal area. It looked brilliant on a draftsman's table, but in the metal, it required a terrifying level of mechanical complexity. As Napier developed the 16-cylinder Rapier and the 24-cylinder Dagger, the reality of the H-block tore through the Acton machine shops. The new engines required a staggering number of small, highly stressed gears, bearings, valves, and moving parts. The machinists who had spent the 1920s mastering the heavy, durable, reliable aluminum castings of the Lion were now asked to build intricate clockwork mechanisms that spun at terrifying speeds. The consequences rippled outward into the service network. On RAF airfields, the mechanics who had trusted the Lion implicitly found themselves fighting a losing battle against the new Napier H blocks. The Dagger was notoriously difficult to cool, prone to catastrophic oil leaks, and demanded punishing, meticulous maintenance schedules. The trust that Napier had spent a decade building with British ground crews began to evaporate in a cloud of overheating oil. By the mid-1930s, the Air Ministry's patience with Acton was wearing thin. As Britain began rearming in the shadow of a second global conflict, government contracts flowed away from West London. Rolls-Royce dominated the fighter market with the Kestrel and the legendary Merlin V12, offering the perfect compromise of aerodynamics, power, and reliability. Meanwhile, the Bristol Aeroplane Company was capturing the heavy bomber market with the sleeve valve radial engine, a piston aircraft engine with cylinders arranged in a circle, using moving sleeves instead of conventional poppet valves to control gas flow, removing the need for complex overhead valve trains. Napier found itself squeezed out of the very industry it had once ruled. Production of new Napier Lions for frontline military aircraft slowed to a crawl and then stopped entirely. The assembly lines at Acton were reconfigured to chase the impossible H-block dream, leaving the W12 as a legacy product. But while the Air Ministry no longer wanted the wide, heavy engine in the sky, the Lion had not ceased to exist. It simply fell down the industrial food chain, moving into a strange second life, where its massive cast iron and aluminium bulk was no longer an aerodynamic penalty, but a cheap, brute force advantage. As the Royal Air Force transitioned to sleek, aerodynamic monoplanes powered by Rolls-Royce and Bristol, the Napier Lion was quietly pushed out of the hangars and down to the coastline. The Air Ministry still had hundreds of reliable, heavy-lifting W12 blocks in its inventory, and they found a new purpose in the hulls of high-speed launches, military rescue boats designed to race out into the English Channel and pull down pilots from the freezing water. Marinized by Napier and rebranded as the Sea Lion, the engine proved incredibly resilient in this harsh new environment. In British boatyards, mechanics bolted these massive aluminium blocks deep inside wooden hulls, where they were subjected to punishing, wide-open throttle runs across heavy seas and the constant, corrosive assault of salt water. The engine that had once represented the absolute cutting edge of British aviation was now a utility motor, doing the wet, unglamorous work of coastal rescue. Simultaneously, a very different kind of secondary market opened up. In the 1930s, as the military steadily decommissioned its older Lion-powered aircraft, the engines flooded into the British surplus market. They were bought up for fractions of their original cost by independent mechanics, garagistas, and speed record chasers working in cold, drafty sheds around Brooklands and the Midlands. This was a profound shift in the engine's meaning. When Malcolm Campbell or Henry Seagrave raced Lions in the 1920s, they were driving state-backed, factory-supported pinnacles of national pride. But when men like John Cobb began building cars like the Napier Railton in the 1930s, and later the Railton Mobile Special, they were operating on scrapyard economics. They chose the Lion not because it was the future of engineering, but because it was a 24-liter sledgehammer of cheap, readily available power. The broad aero architecture that was too wide for a fighter plane was perfectly acceptable when buried inside the cavernous bodywork of a 4-ton land speed record car. The Lion had become the ultimate hot rod engine of the British interwar period, a terrifyingly powerful cast-off. Back at the Acton factory, the situation was turning desperate. The decision to abandon the W12 and leap into the complex H-block architecture was tearing the company apart. The ultimate expression of this panic was the Napier Sabre, an immensely powerful 24-cylinder, liquid-cooled, sleeve-valve H-block engine designed for the Hawker Typhoon. On paper, the Sabre was a 2,000-horsepower miracle of low frontal area. In reality, it was a production nightmare. The machining tolerances required for the Sabre's sleeve valves and complex gearing were beyond the stretch capacity of Napier's traditional workforce. The engines suffered catastrophic failures, oil leaks, and seized sleeves. The trust that Napier had spent 2 decades building with the Air Ministry shattered. Mechanics on wartime airfields cursed the Sabre's maintenance demands, longing for the simple, heavy reliability they had once known with the Lion. By 1942, in the middle of the Second World War, the British government lost patience with the Acton management. The Ministry of Aircraft Production intervened directly. They concluded that Napier Son could no longer be trusted to manage its own engineering and production lines. In a quiet, bureaucratic, but devastating move, the government forced the independent company to be absorbed by English Electric, the proud autonomous engineering house that A.J. Rowledge had transformed in 1917, the company that had abandoned luxury motor cars to conquer the skies, and the factory that had made Britain the fastest nation on earth, ceased to exist as an independent entity. Acton became just another subsidiary plant in a vast, faceless industrial conglomerate. The Napier Lion, the engine that built the empire, outlived the independence of its maker. But the world it was built for had already vanished. The skies now belonged to the Rolls-Royce Merlin. The future belonged to the jet engine. The heavy cast-aluminium W12s were left behind in marine sheds and surplus yards, waiting for the scrapyard or the museum. The engine still ran. The frontline orders stopped. The aerodynamic rules changed. The government contracts moved to Derby. The Acton factory lost its independence. The W12 became cheap surplus metal. The badge remained. The aviation empire it built was gone. The engine was formally retired from the skies, but its physical presence in Britain was too heavy, too loud, and too powerful to simply disappear. The name Napier Son did not survive the transition into the modern aerospace era. After the forced acquisition by English Electric in 1942, the Acton factory was entirely stripped of its independence. Napier was reduced to a subsidiary, tasked with building complex, highly stressed projects that other firms avoided, like the incredible Napier Deltic diesel engine for locomotives and fast patrol boats. But as a premier builder of frontline aero engines, their time had definitively passed. In the 1960s, English Electric's aero engine division was absorbed by the very rival that had defeated the Lion at the Schneider Trophy, Rolls-Royce. The Napier name, which had once commanded the skies and rivaled the best engineering houses in the world, was quietly dissolved into corporate consolidation, surviving only as a badge on a line of industrial turbochargers. The great aviation empire was dead, but the line itself refused to die. Today, the engine survives in a vibrant, fiercely dedicated British preservation community. If you walk into the Beaulieu National Motor Museum in Hampshire, or stand in the historic paddock at the Brooklands Museum in Surrey, you will not find the Napier Lion hidden away as a forgotten failure. You will find it celebrated as the ultimate expression of interwar British speed. In these transport museums, the W12 blocks sit proudly inside the cavernous chassis of land speed record cars, carefully maintained by mechanics who still understand the dark art of balancing 3 carburetors on a 24-liter block. The most famous surviving example is the Napier Railton, the legendary track car commissioned by John Cobb in 1933. When the Brooklands Museum brings this car out for dynamic displays, it does not sound like a museum piece. It sounds like an act of violence. The unsilenced exhausts bark with a deep, percussive thunder that shakes the ground, spitting unburnt aviation fuel and leaving the heavy scent of hot oil in the air. For the enthusiasts, restorers, and volunteers who keep it running, the Lion is not just a piece of metal, it is a living, breathing connection to a time when Britain built the fastest machines on Earth. This survival passes what we might call the not nostalgia test. The reverence for the Napier Lion today is not simply a romantic longing for the 1920s. A Napier Lion sitting in a museum case is a physical argument about how engineering used to solve problems. In the modern era, where efficiency is dictated by software-controlled powertrains, battery power, and wind tunnel aerodynamics, the Lion represents a radically different philosophy. It is the ultimate monument to the era of displacement, a time when British engineers believed that if an aircraft or a car needed to go faster, the answer was simply to cast more aluminium, bore larger cylinders, and force more fuel into the combustion chambers. The Lion matters because it shows the absolute zenith of mechanical brute force, right before aerodynamics and the jet engine changed the rules of physics forever. The industrial landscape that created this brute force is long gone. If you travel to Acton Vale in West London today, you will not find the sprawling factory complex that once poured the alloy for the Schneider Trophy winners. The foundries have been demolished. The machining lines where men in flat caps milled steel connecting rods have been replaced by modern office blocks, retail parks, and residential developments. The town that built its identity around the roaring W12 no longer produces engines. The vast service network, the military depots, the marine boatyards, and the parts counters that once kept hundreds of Lions running across the British Empire has vanished. All that remains of the Acton workforce's incredible skill are oil-stained service manuals, carefully preserved in the archives of marked clubs and historical societies. Yet there is a strange, surprising footnote to the story of the broad aero architecture. For decades, the W12 layout was dismissed as a heavy, wide aerodynamic dead end. But at the turn of the 21st century, when the Volkswagen Group acquired Bentley and wanted to build a new generation of ultra-luxury Grand Tours at the Crew Factory, they needed an engine that was incredibly compact but immensely powerful. Their solution was the W12. The modern Bentley W12 was infinitely more refined, liquid-cooled, and twin-turbocharged. But the fundamental geometric concept, arranging cylinders in a W to keep the crankshaft short and the block compact, was exactly the same mechanical solution A.J. Rowledge had drafted in Acton in 1917. The industry eventually realized that Napier's architecture was not wrong. It just belonged in a luxury car, not a fighter plane. The Napier Lion was a machine born of necessity and killed by progress. It was an engine that taught a recovering nation how to trust aluminum, how to master massive displacement, and how to push the boundaries of absolute speed on land, sea, and air. It was a victim of its own strength, trapped by a shape that was perfect for 1918, but impossible for 1938. Somewhere in the quiet halls of the Brooklands Museum, a 24-liter Napier Lion W12 still sits on an engine stand. The massive aluminum castings cold under the display lights, the triple bank shape defiant, holding the memory of a time when British power was measured not by software, but by the sheer, deafening force of 12 cylinders tearing through the air. See you in the next one.